Hello, sixth grade students. It has been somewhere in the neighborhood of 5.5, 6 months since I've had to do any kind of teaching like this. So if I'm a little rusty, please excuse me. It's also probably pretty weird right now because I'm telling you to watch me on your screen when I'm probably right up here at the front of my room. But hey, that's how things are going to work from now on. So if you're in here in the classroom, you can pause this presentation at any point in time and ask me a question. I'll be up here at the room. And if you're at home, because we're in a remote situation, we'll have live sessions where you can ask me questions about any of this. But for now, this is kind of how things are going to work. So watch this video. There'll be some questions about at the end. It'll be about something that's been in this presentation. So today we are going to be looking at the topic that's on your screen. What is everything made out of? Like in the entire universe, what is everything made out of? And this is something that has been bugging people for literally thousands of years. They have going back thousands of years, people have been trying everything they could to answer the question, what is everything made out of? They started off with some really terrible ideas, and let's take a look at those. So we're going to be using our definitions for this lesson. We're going to introduce you to them, but we're also going to be using these definitions throughout the entire year. So our short-term goal is to get us used to certain vocabulary words that we have to use all year. A lot of the words that you're going to see today show up in every single quarter this year. So in the third quarter, when we get to cells, or the fourth quarter, when we get to rocks, minerals, and soil, we're still going to be using these words. So we have to have a good understanding of what they are and what they mean. In the next couple of weeks, you are going to be able to start using these words in classroom conversations. So that's our medium-term goal, is to get you comfortable in this unit of figuring out the differences between these words. And then in the long term, we're going to be using these words to problem solve in the third and fourth quarter. So let's get on to a very bad idea. So thousands of years ago, the Greeks were trying to answer the question of what is everything in the universe made out of? And what they settled on, and this is a bad idea, but it got science started, was everything in the universe was made out of the four things you see on your screen: fire, earth, air, and water. They believed that everything in the universe was made out of a particular combination of these four, what they called elements. Using the four elements, everything in the world and universe could be made. And everything had kind of like its own formula for how to make anything out of these four. So if you had a certain percent of fire and a certain percent of earth and a certain percent of air and a certain percent of water, when it all added up in just the right way, you could get a carrot. So they believed that a carrot was made out of earth, fire, air, and water in just the exact right combination. If you took these four elements, earth, air, fire, water, you could change the percentages a little bit and get a new and different substance. And for example, a piece of gold. Now, a carrot would probably be made out of more earth and water than air and fire, whereas a piece of gold might be made more out of more earth and fire because it's, a rock and it's shiny and wouldn't have as much air or water in it. So by playing around with the percentages and the amounts of each element, you could get different substances. If you got a certain amount of air, earth, fire, and water, and you change the percentages to be just right, you could get a chicken. Yeah. And probably what they were most after was trying to figure out what percentage of all of these four elements you needed to get probably the most desirable, beautiful substance ever known to humankind. If you took the exact amount of fire, just enough earth, the right percentage of air, and the exact amount of water to balance it all out, you could get the most glorious substance in the known universe. So clearly this was a terrible idea. The world and the universe is not made out of earth, fire, air, and water. But it did at least get the conversation started, and that was important. Scientists got pointed in the right direction. And the big difference between the ancient Greeks and us is that we just have better technology and we can see a better picture of what is going on. So with our current technology, we can actually literally see what everything is made out of. So let's go back to the carrot. It is not made out of earth, fire, air, and water. But we have things that can now allow us to zoom in closer, microscopes, magnifying glasses, things like that. And as we get closer to the carrot, we can actually see that it's made out of smaller parts. And if we zoom in even further, we're actually looking now at something we're going to be looking at in the third quarter. Carrots are made out of cells. But cells themselves, if you have a good enough microscope, seem to be made out of smaller things themselves. Here we have something called a mitochondria. We'll get into this in the third quarter. But when we zoom in on a mitochondria, we can see the mitochondria is made out of smaller parts. And if we keep zooming in, we get to this point. At this point, everything seems to be made out of these tiny little fuzzy looking vibrating spheres. They don't sit too terribly still. They sit and they vibrate in place. But everything that we look at, we eventually get to the same point, these fuzzy little spheres. And with our microscopes, we are able to see these fuzzy little spheres in everything. So to get an idea of just how much we zoomed in, let's take one of your rulers. Now, rulers for us in the United States, we tend to use inches, but the rest of the world uses centimeters, and that's what science uses. So let's look at centimeters. So if you look at a centimeter end of a ruler, you can see the big marks are 1 centimeter, and centimeters seem to be divided into these tiny little markings called millimeters. So let's take a look at that. So here we have centimeters and a millimeter. Well, these fuzzy little spheres, just how big are they compared to a millimeter on your ruler? Well, let's zoom in. So now a millimeter is about that big. And a millimeter can be broken into 10 even segments called a micrometer. So now let's zoom in on a micrometer. So this dot here is a millimeter. This dot here is a millimeter. So from here to here is a micrometer. Now micrometers can be broken down into nanometers, okay? Ridiculously small. So let's go back to these fuzzy little spheres. How big are these fuzzy little spheres? Well, they are around 0.14. This is the distance between them. So these things are actually less than 1/10 of 1 nanometer. These things are very, very small. But if you look at the screen, you can see these fuzzy little spheres, and these are really about the best pictures we can get because they don't sit still very well, and we're so zoomed in that any kind of movement makes the image blurry. This is actually the most magnified image ever produced of these fuzzy little spheres. So if you really want to get rich and famous, come up with a better way of filming these things. All right, so carrot, when we zoomed all the way in, we got to the fuzzy little spheres. Now let's take something that's not considered alive, a rock. So we zoom in on the rock. We zoom in a little bit more. We're not going to see cells at this point because rocks aren't made of cells, but we get to this point, and here we have this distance is about 10 micrometers. And sure enough, we seem to get to these fuzzy little dots. So no matter what we look at when we zoom in, it really seems that everything in the universe is made out of these fuzzy little dots. So scientists have concluded that everything in the universe is made out of these fuzzy little dots. So it's time to give a name to these fuzzy little dots. Ladies and gentlemen, I give you the atom. Atoms are the smallest, most basic unit of matter. That means that atoms are the building block of everything in the universe. Whether it is a star that is tens of millions of light years away, or something that's inside your pocket, it is made out of atoms. Everything in the universe is made out of these atoms. Now, the word atom comes from a Greek word, atomos, which means unbreakable, uncuttable, unsplittable, something like that. And that basically means that you can't get anything further than an atom. You can't basically split apart an atom and make anything out of those parts. Okay. Now, if you go to Google Images and you type in the word atom, you are going to see all kinds of terrible information. So let's break down what's good and what's bad about some of these diagrams. So here we have a basic diagram of an atom, and there's actually a lot of good things about this atom. The atoms tend to have a central core area that's called the nucleus. Inside the nucleus are two different kinds of smaller parts. So we're going to say particles for smaller parts. The two types of particles in the nucleus are the neutrons and the protons, and we'll get into those in just a little bit. And outside of the core area, in like this cloud area, are particles called electrons. So atoms are made out of smaller things, but these smaller things, protons, neutrons, and electrons, by themselves can't really make matter. I can take atoms and I can make a chicken. I can take atoms and I can make a kitchen sink, but I can't take just protons and make a chicken. I can't take just neutrons and protons and make a carrot. So you need these three parts working together to make atoms, and then out of atoms, I can make anything in the universe. If you look at the definition that is in your packet, the definition of a proton is a particle, small part, in the nucleus of an atom. So here we have protons, and you can see they live in this nucleus region of an atom, and they have a positive charge, which is why all of the protons in here have a plus sign on them. So anything in this diagram with a plus sign is a proton. How many protons do you see? Well, 1, 2, 3, 4, 5, 6, 7. So there are 7 protons in this diagram, and that's going to be important later. The next definition we need to work with is a neutron. A neutron is a particle in the nucleus of an atom with a neutral or no charge. Scientists actually kind of argue whether to call it neutral charge or just not having a charge at all. So we're going to say both, just so that both scientists groups are happy. Now, neutrons, in this diagram, it looks like there are also 7, but as you get into larger atoms, the neutrons don't really equal anything. They actually can be the number one particle as far as amount of particles in an atom. So neutrons will be in the nucleus always, unless something's gone terribly wrong, and they don't have any kind of charge at all. And our last definition today is electrons. Electrons, if you look at our definition, is a particle in the electron cloud. Electrons do not exist in the nucleus, and again, unless something's gone horribly wrong. And they have a negative charge. So on all of our electrons out here in the electron cloud, you can see that they are negatively charged. Now, how many electrons do you see? Well, 1, 2, 3, 4, 5, 6, 7. There were 7 protons, and there were 7 electrons. 7 positively charged particles, 7 negatively charged particles. And for most atoms, that's what's going to be the case. Atoms like to be neutral overall. So if you have more protons than you do electrons, you have a positively charged atom. Or if you have more electrons than you do protons, you have a negatively charged atom. But most atoms in the universe are neutrally charged. So there is a balance between protons and electrons. All right, so now let's look at some goods and some bads of some diagrams that you will come across. So here we have protons and neutrons in the middle and electrons on the outside. There are 2 protons, there are 2 electrons. This is pretty much a good model of an atom with one major bad flaw. When scientists were first figuring out about protons, neutrons, and electrons, they knew that protons were in the middle, and they knew that electrons were on the outside, and electrons seemed to be moving. So they tried to think about, what in my world is this similar to? Well, a scientist thought, this kind of reminds me of a solar system, where the sun is in the middle and the planets are like in an orbit. Well, atoms must be like that too. So in the middle would be the proton, and the electrons are like in an orbit. And so he drew a model of the atom like this, with an electron in like this orbit pattern. And turns out that that's actually really wrong. Electrons actually move around very randomly, and they don't have any kind of orbit system at all. So if you see a model of an atom with this fixed orbit system, just know that that's garbage. All right, so here we have another model. And I don't know which ones are protons and which ones are neutrons, but let's see if we can figure this out. There are 1, 2, 3, 4 electrons, and 1, 2, 3, 4 red particles, and 1, 2, 3, 4, 5 white particles. And so that means that because protons and electrons are usually in balance, that the red particles here must be the protons, because that way 4 and 4. This is another example of electrons being in this fixed orbit system, like planets going around a sun, which is nonsense. All right, this is wrong for a lot of reasons. Number one, the electrons are in orbits. That's bad. But 1, 2, 3, 4, 5, 6 electrons, and I don't care what color you're counting for what, whether it's gray or black on this screen, these protons and neutrons are very out of balance with the electron cloud. So this is an even worse one. Here we have a big pile of garbage for a diagram of an atom. Electrons in fixed orbits. We have electrons the same color as protons or neutrons, I'm not sure, but either way, that's nonsense. This just makes me physically angry. All right, so your fact of the day. The entire internet is stored and delivered using 540 billion trillion electrons. Electrons are so small that 540 billion trillion electrons is about 50 grams, or the weight of one strawberry. So the entire internet weighs about as much as a strawberry. All right, that is enough for your first lesson. Most of them I'm going to try to keep shorter than this, but we've got a lot of groundwork to lay out. And then from there, the little bits of information will hopefully be a bit shorter. All right, it's now time for you to answer some basic comprehension questions. I've given you about 5 questions to answer for all of these activities. I'm not going to ask you something that's really not on your screen. I'm either going to say something or it's going to be written on your screen. So you can always go back and find the answer if you're not too terribly sure. If we are in a situation where you're actually in the classroom with me, just raise your hand and ask a question about anything that you want to ask about or clarify. If you have an extension question, something like that. If we are in a situation where you're at home or I'm at home or we're both at home, we're going to have live sessions and stuff like that for you to be able to ask questions. Okay, so the big idea here is when you go back and you're looking for the answers to these questions that are attached to this lesson, do not answer a question until you found the answer. And if you can't find the answer, don't answer it until you've communicated with me some way. And that way we can make sure that everybody gets good grades and is learning what they need to do. All right. So thank you very much for listening. And hopefully you can find all these answers. Bye-bye.